Hi guys, the homework for 8.1, but there are going to be 3 times homeworks from 8.1, right? This is about the quadratic homogeneous case, and in fact the one where we have 2 different roots. We discussed in the lecture today what happens if you have quadratic but the same roots. The first one was 4a, and the equation, the recurrence relation was an is an minus 1 plus 6 times an minus 2, and then we initial conditions was a0 is 3 and a1 is 6. Okay, the first thing, remember, was the characteristic equation. Well, again, perhaps in general, of course, you should perhaps establish what degree are we talking about here, and you can see that since we have to go back 2, we have to go to a n minus 2, the degree is 2. So it truly is quadratic. It's also, by the way, linear, because there are no powers of these a-n's. There is no products. It's also with constant coefficients. So it all fits exactly on what we were doing. So the characteristic equation is r squared equals r plus 6. I like to write it this way so that I don't make any minus signs. And then I can bring it to the other side, r squared minus r minus 6 equal to 0. So how does it work again? Remember, you kind of have to work your way up if you want. The last one is the constant. The next one will be degree 1, and this would be the degree 2 part. So here you would have r to the 0, this would be r to the 1, and this would be r squared. And meaning to say you replace the AIs by these various powers of r. Okay, what you actually really do is replace an by r to the n, n minus 1 by r to the n minus 1, and by rn minus 2, and then you factor out an rn minus 2. But that's the same, the result is the same. Okay, so we have to solve this. Step 2 is solve this equation. And so that factoring, we have to find 2 factors that give negative 6 if you add them and negative 1, if you multiply them, and negative 1 if you add them. So I think minus 3 and plus 2 would do the job, right? Yeah, okay. Is 0, so we know that r is 3, and this tells me that r is negative 2. Okay, so step 3 is then proposing a solution. We know that a general solution will always look like, so an will look like a coefficient alpha 1. I'm going to use, I don't like to write too many things, so I'm writing just alpha 3 to the power n plus beta, let's use a little bit more of the Greek alphabet, minus 2 to the power n. You take these roots and you take the exponential function with that base. Good. And then the final thing, step 4, now we have to use our initial conditions. So a0 is 3, that means that I plug in n equals 0 in this case, right? And that will give me, a 0 power is nothing, so alpha plus beta. And if I do a1 is equal to 6, now I plug in 1, that gets 3 alpha minus 2 beta. And then I have several methods of solving this thing. So we solve this now, and I'm going to do substitution here. I solve for alpha in this equation, so I see that alpha is 3 minus beta, and I can plug this in here. 6 is then 3 times 3 minus beta minus 2 times beta. That is 9 minus 3 beta minus 2 beta. That is 9 minus 5 beta. Let's bring 5 beta to this side and 6 to this side. So I find that beta is 3/5. Well, it's a fraction, that can happen, there's nothing wrong with that. And to find then what alpha is, I use that. Alpha is 3 minus 3/5, that is 15 minus 3/5, that would be 12/5. And so the general solution would be an is where are we? 12 alpha, that was a coefficient, 12/5 3 to the power n plus 3/5 minus 2 to the power n. Okay, and you can always check that at least the initial conditions are true. If if I put n2 equal to 0, then I get 12 fifths plus 3 fifths, that is 15 fifths, which is 3. And if I put in 1 in both, then I get 36 fifths. I put now n is 1, so they get 3 times 12, and then minus 6 times 5, that is 30 fifths, that is 6. So that's just double checking that I got these fractions. They will happen. They can happen. So just because you see a fraction, you don't think you're wrong. But I'll try to avoid them as much as I can. Okay. Okay, that was that, and then the other one was for E. For E, and that was the equation, the recursion equation. An is an minus 2. Is this of the form that we're discussing? Yes, because you have to go 2 back. You say, well, you don't have to go back 1 back. No, okay, fine, but you do have to go 2 back. So the degree is 2 here. And what are the how many initial conditions? You might think, oh, there's only one. I go only back 1 to an. Sorry, I only go back to an minus 2, so I only need 1 initial condition. No. The number of initial conditions is always equal to the degree. So in this case, the initial conditions that were given were a0 is 5 and a1 was negative 1. Okay, so what happens here? Well, let's work it out. Step 1. The characteristic equation. Remember, this thing becomes r squared. There is no term that would give me the linear part. The only thing I have as a constant part is 1. So r squared is 1, and then by the root property, there are 2 roots, of course, the positive 1 and negative 1. That are the 2 roots. Of course, you can also factor. You can also write r squared minus 1. That is r minus 1 times r plus 1, and you get to the same conclusion. Okay, so we have 2 roots. So this step 2, that was step 2. So step 3 is now the proposed solution. An is equal to, you take alpha times 1 to the power the first root plus beta minus 1 to the power the next root. Minus 1 to the next root to the power n. I'm saying it wrong. Notice that actually this is a bit weird, right? Because the 1 to the power n actually doesn't really do anything. It's alpha plus beta to the minus 1 to the n. This is not a very interesting sequence if you think about it, because what is going to happen here? The minus 1 to the power n is either minus or plus. So the result is either alpha minus beta or alpha plus beta, depending whether n is even or odd. Kind of a boring sequence. It just alternates between 2 numbers. Which 2 numbers? Well, let's figure it out. Actually, we know what the 2 numbers are, namely 5 and negative 1, but what is alpha and beta? So step 3, we use the initial conditions to figure out what alpha and beta are. Alpha a0, that is 5, that is alpha plus beta, and a1 is negative 1, that is alpha minus beta. So let me do here the technique by elimination, because if I add the 2, I see the betas cancel, right? So if I add these 2 equations, these 2 betas cancel. I put already the line underneath there to say that's what I'm going to do. So 5 minus 1, that is 4, that is 2 alpha, and the betas cancel. So I'm adding this, right? So this plus that. And from that I see that alpha is 2, and therefore if I plug it in now in one of the, it doesn't matter what, let's plug it in the first one. I say 5 is 2 plus beta, so I see that beta is 3. Okay. Alright, so the general solution an is equal to 2 plus minus 1 to the power 2 plus minus 1 to the power 3. And therefore it alternates between 5 and negative 1, depending on whether n is even or odd. Okay, but that's a recurrence relation, and we have to consider it as a valid recurrence relation because it might occur in particular circumstances. Okay, somehow I did now the easiest of all parts. Okay, and the rest will now be that we'll see in the next homeworks with more complicated calculation. Well, not much more complicated, but well, okay.